All right, everyone, get ready to dive into a real head scratcher. Today, we're talking about the nature of light. Specifically, we're going to be tackling this paper you sent over. It's by physicist S.A. Rashkovsky. And he's making a pretty bold claim. He says photons, those tiny particles of light that we all learn about, those might not actually exist.
Yeah, it's definitely a provocative idea, to say the least. I mean, the concept of the photon is so fundamental to physics, but Rashkovsky isn't saying that light itself isn't real. He's more interested in how we interpret it. Like, do we really need the concept of a photon to explain how light behaves?
It's a good question.
Oh.
Because I don't know about you, but I was taught that photons are everywhere. They're like the building blocks of light. They explain how the sun gets its energy to us, how our phone screens display images, everything.
Right. And we're all familiar with that whole wave-particle duality thing, too. Like, sometimes light acts like a wave, sometimes it acts like a particle. It's weird, but that's the standard model. But what Rashkovsky is suggesting is that maybe light is really just a continuous wave, like a classical wave, and all those quantum effects we see are just a result of how this wave interacts with matter, not because it's made up of particles.
Okay, so instead of picturing light as this stream of little bullet-like photons, we should be thinking of it more like ripples spreading out on a pond. That's kind of a cool way to visualize it, but then how do you explain all those classic experiments that seem to prove light is made of particles? Like the photoelectric effect, for example.
Yeah.
You shine light on certain materials, and it knocks electrons loose, as if a photon had just slammed into them.
And that's one of the experiments that Rashkovsky tackles head-on in his paper, and it's where things get really interesting. See, the usual way to explain the photoelectric effect is to use what's called the Born rule, which relies on the idea of photons. But Rashkovsky, he goes in a different direction. He uses something called the Fermi golden rule.
The Fermi golden rule.
Yeah, it's this principle derived from classical wave theory, and he shows that it can actually accurately predict how much energy those ejected electrons will have based solely on the frequency of the light, not its intensity.
Wait, so you're saying we can explain one of the most important experiments that supposedly proves the existence of photons without ever needing the concept of a photon? That's kind of blowing my mind right now.
It's pretty wild, right? And it doesn't stop there. The paper also goes on to explain other phenomena that we usually attribute to photons, like the Compton effect, even the double-slit experiment, and all without ever invoking the idea of a light particle.
So what we're seeing is that there's this whole other way of explaining all these experiments that we've been told are the cornerstones of quantum mechanics. And it all starts with just rethinking what light really is. It makes you wonder how much our initial assumptions influence how we interpret scientific findings. But you know what really caught my eye in this paper? It was the section on Wiener's experiments. I'm not sure if most people are familiar with those, but they're kind of crucial to this whole debate. Can you tell us a bit about them?
Yeah, Wiener's experiments are fascinating. They deal with these things called standing light waves. So picture this. You have a light wave bouncing back and forth between two mirrors. Now, when the peaks and troughs of the wave interfere with each other, they create this pattern of bright and dark regions. Now, if light were made of these individual photons, like little marbles or something, you'd expect them to just be scattered randomly within that standing wave pattern, right?
Right, like if you toss a handful of marbles into a room, they wouldn't suddenly arrange themselves into some neat and tidy pattern. They'd just land wherever.
Exactly. But that is not what Wiener observed. He used photographic plates to detect the light, and what he found was that only very specific regions of the plates were exposed, and those regions corresponded to the peaks of the standing wave.
So it's like those supposed photons somehow knew where to go. Like they were being guided by the wave itself. That seems a bit strange, doesn't it?
It does seem counterintuitive, right? And this is where Rashkovsky's explanation gets really mind-bending. Because instead of thinking of it as photons bunching up in those bright regions, he suggests it's actually the wave itself that's interacting with the photographic plate in a way that just makes it look like individual particles hit it.
Okay, so walk me through this. How does he explain those very specific exposure points on the plate if it's not photons hitting those exact spots?
Well, remember that Fermi golden rule we were talking about earlier? The one that could explain the photoelectric effect without needing photons?
Yeah.
Well, he uses it here too. He models the photographic plate as a collection of atoms, and each one of those atoms can be excited by the light wave. But here's the key. The probability of an atom being excited is highest where the wave's amplitude is greatest.
So at the peaks of the standing wave.
Exactly.
I think I'm starting to get it. So it's not that the photons are somehow, like, concentrated in those bright regions.
Right.
It's more like The wave itself is just more likely to interact with the plate in those specific areas.
That's a great way to put it. The photographic plate is basically sampling the continuous wave. And because of the way the wave interacts with the atoms, that sampling creates this illusion that we're seeing individual photon hits.
It's like, what's a good analogy?
Yeah.
It's like you threw a bucket of water at a grid, you get this pattern of individual splats, right? But that doesn't mean the water itself was ever divided up into these little splat particles.
That's a perfect analogy.
And this paper is arguing that maybe light behaves in a similar way.
Exactly.
That's such a cool way to think about it. It's so much more intuitive than trying to imagine these particles just magically knowing where to go. But, okay, let's say we ditch the whole photon idea. Doesn't that create other problems? Like, what about Heisenberg's uncertainty principle?
Ah, yes, the uncertainty principle.
That's like quantum mechanics 101, right?
Yeah.
It says you can't know both the position and momentum of a particle with perfect accuracy at the same time.
Right.
And that's often used to justify this whole wave-particle duality in the first place.
It's true, the uncertainty principle is often brought up in this context. But Rashkovsky makes the case that even this fundamental principle of quantum mechanics might actually have a classical explanation when it comes to light.
Wait, hold on. You're saying Heisenberg's uncertainty principle, this cornerstone of quantum weirdness, might actually be not that weird. Okay, now you have to explain that one.
Okay, so think about a wave packet, just a short burst of a wave. Now, to create this short burst, you need to combine multiple waves, each with slightly different frequencies.
Sure.
And the shorter the pulse, the wider the range of frequencies you need to use.
That makes sense. It's like with sound, a really short, sharp sound needs a broader range of frequencies than a long, drawn-out tone.
Exactly. You're getting it.
Okay, I'm following so far.
Now, here's where it connects to the uncertainty principle. When we talk about a photon's momentum, what we're really talking about is related to its wavelength, which is directly tied to its frequency. So if you have a wave packet that has a really well-defined position, meaning it's a very short burst, it must contain a wide range of frequencies, and therefore a wide range of possible momenta for those supposed photons.
So it's not that we can't know both the position and momentum at the same time. It's that a short burst of light inherently has a spread of momenta because of its wave nature. We're not limited by some fundamental quantum fuzziness. It's just a property of the wave itself.
You got it. And Rashkovsky's point is that the uncertainty principle, at least when applied to light, might simply be reflecting this very basic property of classical waves, not some spooky action at a distance or some limit on what we can know.
Okay, I'm starting to see how this all ties together. If we can let go of this idea that light is made of these individual particles, a lot of these quantum effects that seem really strange and counterintuitive, they suddenly have these much more intuitive explanations that are grounded in how waves behave.
Right. It's a very different way of thinking about things.
It really is, but it's exciting. But what does it mean for our understanding of the universe if we can explain light without photons? This is huge. So if light might not be made of these discrete particles we call photons, does that mean other particles are up for debate?
Well, it certainly opens up some interesting questions. If we can explain so much about light, one of the most fundamental things in the universe, if we can explain it using classical waves without needing these particles, it does make you wonder about our current models of other fundamental particles, like electrons, for example. Could those also be explained in a different way? Maybe we're not seeing the full picture yet.
So you're saying this one paper about light could potentially unravel our understanding of matter itself?
Potentially. It's a pretty radical idea, but that's what makes it so exciting.
It is exciting, but I'm also guessing not everyone in physics is ready to throw out the photon just yet.
Oh, absolutely not. It's definitely an ongoing debate, Rashkovsky's work is challenging a very deeply ingrained assumption in physics. And as with any scientific theory, it's going to be scrutinized, it's going to be debated, people will try to find holes in it.
That's how science works.
Exactly. It's a process. And it's important to remember that Rashkovsky isn't claiming to have definitively proven that photons don't exist. It's more like. What he's done is he's offered a very compelling alternative perspective, like a new lens through which we can view some of these really fundamental mysteries of the universe.
It's a good reminder that science isn't about being right or wrong. It's about finding the best explanation, the most elegant, the most accurate way to describe what we observe.
Absolutely. And what makes this paper so thought-provoking is that it forces us to do exactly that. It makes us look at familiar phenomena, like light, in a completely new way.
And maybe question some of our most cherished scientific concepts.
Exactly. It's about being willing to re-examine what we think we know.
So, as we wrap up this incredible deep dive, What's the one big takeaway you want to leave our listeners with?
I think the biggest takeaway is keep an open mind. Our understanding of the universe is constantly evolving, and often the most groundbreaking insights, the biggest leaps forward. They come from daring to question even our most fundamental assumptions. And I think Rishkovsky's work is a perfect example of that. He's reminding us that there's always more to learn, and sometimes the most satisfying answers are the ones that challenge us to think differently.
And who knows, maybe one day the idea of a photon-free universe won't seem so radical after all, right?
You never know.
If you've enjoyed this deep dive as much as we have, and we certainly did, we encourage you to check out Rishkovsky's paper for yourselves. We'll be sure to link it in the show notes. And until next time, keep those questions coming, and most importantly, never stop exploring the universe and all its mind-bending mysteries.